All right, let's get started. First, I have an apology. I went onto Piazza, and all of a sudden, there were all these messages that I had not responded to. And normally, Piazza notifies me on the phone whenever messages come. So something has gone wrong in my settings, and I wasn't getting those. So I responded to one or two. I'll respond to the rest of them in the cafe. But again, my apologies. And there was one I saw right where code was posted, and so they did a private post, and that makes perfect sense if you're actually providing code. But for anything else where you're not providing code, try not to make it a private post, because it almost certainly someone else will have that question. You have a question? No? You didn't raise your hand? You made me move that paper like that. I got confused. All right. Office hours. Today, let's say to 2:30 to 3 plus. So if people are there, I'll still stick around. And that would be in the cafe. And tomorrow, 1 to 4 in my office. All right. So feel free to come by. I'm happy to help with any questions on the program assignment. The program assignment, just as a reminder, if the numbers you are getting, let's see, for the very first problem, is that what it is, Josh? For the very first problem, don't quite match mine in the sense that yours is more precise than mine. That's because my initial version did not match the code. So I had a 1 e to the minus 3, I think, is my initial stopping point, and that's what I copied the numbers for, and then change it to 1 e minus 4, and they don't match. So it is updated in Colab. Go look at that. If the numbers aren't matching, it's possible what you did is that you saved a copy before I made that change. I made that change like last Wednesday or something. So you can do it over the weekend. That's not a problem. But just be aware of that. I think that's about it. Let's go over a question from Wednesday. So the question was, and this was back in dynamic programming. So in dynamic programming, if we're doing this asynchronous updating, right? Asynchronous updating is basically, we don't do this full sweep where we sweep through all states and then sweep through all states again and sweep through all states again. But the book said basically, if you have an asynchronous update and a non-discounted episodic, is that right? This was your question you came up with, that there were certain sequences of states you could visit such that didn't converge. And so I thought about that, but not for long enough, because I don't have an answer. So I have some feelers out, and I will revisit this with you. But I'd appreciate some of you also thinking more about that. What could that happen in some non-discounted state? What could come up? So I thought, for instance, just of sort of a loops of states where if we had a loop and we were undiscounted, the sum of the loop would have to be 0, right? In order for us to stay bounded. But I was just trying to think of that loop if we had maybe -1s and +1s. And I didn't get anywhere, but that's kind of what I was thinking to begin with. But anyway, I'll have an answer for you at some point. Let's go ahead and do the quiz, and then we'll continue on with Monte Carlo. I owe you one. Thank you. There you go. Okay. take what time you need to finish it. Turn it in at the end. Give it another minute. Go ahead and pass them on over if you would, please. So this weekend I was reading an autobiography of a British epidemiologist who was one of the first to study lung disease in miners, coal miners. And so part of what they didn't even know was like what sort of exposure to dust and so on decliners have. So they went to a big coal mine, and the way they would measure dust is basically would follow around a miner. Right? There'd be an observer who'd follow around with this apparatus that would somehow accumulate whatever dust exposure there was. And so the question they had was how to do that. Like, who are we going to follow? They couldn't follow everybody. They both didn't have enough observers, and it would slow down the whole mine and everything else. And so they wanted to figure out kind of a representative miner, because miners had different tasks, and they also worked in different mines that had different characteristics in regards to dust. And so what they did is they would randomly determine every day a miner who they were going to follow. And I thought, that is Monte Carlo method, right? You just follow an episode with sort of a day, and it was giving an estimate of the dust exposure for an average miner. And then they just did this for, I don't know how long, a month, 2 months, something like that. But I was intrigued by that. So a reminder, a Monte Carlo method, what we're going to do is generate these episodes, right? So our goal is to estimate the value function, either the state value function or the action value function, and probably the action value function, because that will be useful for policy improvement. And all we really do is just have an agent that's operating under some policy, set it loose in the environment, get back the rewards, and then we've got this entire episode, right? And from that, we can improve our estimate of value functions. So for instance, here, we started in S1, and then went to S2, and then went back to S1. If we're just purely looking at the state value function, it'd be very similar for the action value function. We can come up with an estimate for both S1 and S2, because we visited those, right? We didn't visit any other states. Clearly, we don't have any new information about those states. And so what we could do is just say, what was the total discounted reward we got from, let's say, state S2? Okay, so S2, we got R3, and we got a discounted R2. Calculate that, add it to the averages we've seen already for S2, and that is our new estimate for S2. For S3, it's a little more complicated because we saw it twice, so we have a choice. Do we want to just look at the first time we went to S1 and look at our discounted R3 and R3 again and R2? Or do we want to look at that, which is certainly one valid estimate of S1, and then also look at this other valid estimate of S1, which is we were in S1 here and got an R2.
When you say averages, do you mean the exponentially weighted averages or the regular average?
Just regular old unweighted average of all of the returns we've seen for having been in that state. Okay? So when we have an episode, if we're using first visit, then we have new additional estimates for every distinct state. Or if we're doing action values, every distinct state action pair. If we're using every visit, every single state that we enter gives us a new estimate, right? Does that make sense? Okay. So I talked on Wednesday about the bias that was evident. So basically, the first visit is unbiased, and I can show you that in a moment. I'll show it more by example, actually, with this MDP, although a fairly simple extension of this would make it work with any MDP. But let's just look at this example right here. So we got a 0.5 chance of getting a 1 reward and coming back to S, and a 0.5 chance of getting a 0. Right? So half the time, let's just look at our, what is V of S? And I don't have a policy here because there's no actions, right? For this particular MDP, whatever action you take, this is what the environment does, right? I don't care what you do. So V of S, right, so we don't care about the policy, and we can basically look at the, let's just kind of write it out, S prime comma R of P of S prime comma R given S. I'm going to just ignore A because we don't have an A, of R plus gamma V of S prime. Right, and we got two possibilities here. Either we go back to ourselves, right, so that is a 0.5 chance of getting a reward of 1 plus gamma, and gamma is just going to be 1, so we'll be undiscounted for the moment. V of S, right, because we come back to ourselves, plus 0.5 times 0 plus V of t. And we've said that our rewards for being in the terminal state are 0, so this equals 0.5 times 1 plus V of S. Yes? And so if we solve, then what? 0.5 V of S equals 0.5 V of S equals 1. Is that really what I want to say?
Also 0.5 VT.
Oh, okay.
Yeah, 0, 0.
Yeah, that's right. Wait, no, that's true. Okay, yeah.
That sure looks right. It's just not the number I want, so I may revisit that.
What number do you want?
I'd like 2. Can we get 2?
Yeah, just change 0.5 to 1.
Anywhere I want? Any given 0.5?
No, like the,
geometry.
oh, sorry, no, change the 1 to 2 in the, wait.
Yeah. Well, we'll look at this for a moment. Okay. So
Just make the reward 4.
yeah, well, if I change the reward, I can get there for sure, but I don't want to do that. So let us look at this a second.
To change it, that's gotta be right.
It seems right, right?
That's right, that's right.
All right. Yeah, okay. So if we look at an episode, basically our episode here is going to consist of, SA1, and this is again going over what we did on Wednesday, until eventually we're going to get a 0 and have a t here, right? And let's look at the expectation here in terms of what the reward is. So if we call, let's say, the number of ones k, we're going to have a certain number of ones, and that's going to be the reward we get. Okay? So if we sum over all k's, what does our reward look like? And what's the probability of it? So what's the probability of getting k1s? Alfredo. Right, this is our MDP. What's our probability of getting 0 ones?
0.5.
Okay, and 1 1? Exactly 1 1?
0.5. Wait, how many times are we?
So I want to look at the probability of getting 0 ones. I agree, is we have to take this back, right? That's a 0.5. If we want to get exactly 1 1, then we got to go here and then here, right? And this multiplied probabilities are
0.15 squared. Wait.
0.5 squared, yeah, 0.25, right? So let's look at, so it's 0.5 to the k. So this is the probability of k1s, right? And then what's our reward? If we get k1s, our reward is k.
K plus 1. Yeah.
if we get k1s, then our probability is k plus 1.
Yeah, excellent.
Just to get 1, 1, you need 2.
So if we have 0 ones, 0.5 to the, so if we have 0 ones, the probability of that is 1/2, right? So that'd be 0.5 to the, got it, 1. I'm with you, yes. Okay, so this is our summation. Let's move a 0.5 out. Something like that. Do we know anything about this? I believe there is an identity, and thank goodness I wrote it down because I don't remember it. So that this, basically the summation, k equals 0 to infinity of x to the k equals x over 1 minus x squared. Okay? So this is going to be equal to 0.5 times 0.5 over 1 minus 0.5 squared, which equals? Owen?
Still calculating.
No, don't calculate. Just cancel. We've got 2.5s in the numerator, and we've got 2.5s in the denominator,
Oh yeah. Just
which equals 1, which is good. So it turns out this is what I want. Okay? So this basically shows us that our expectation of using our first visit calculation is our value of our state, right? In expectation. Right? In this particular case, we got a 2. But that's going to happen much less often than getting a 1, and we'll get zeros more, and so on. But it's in expectation is the correct thing. So this is unbiased. Okay, so the expectation of sort of the first visit equals sort of V of S. Okay? If we're doing every, let's stick to positive words for a moment just to make it easier. So if we're doing every, what do we know about the first, so let's take one episode, our very first episode, and compare the first visit versus the every visit, or the average of the every visit, right? Because the every visit will have possibly more than one. In fact, in this case, if we use every visit, Garrett, how many, where are you? There you go.
If we use every visit,
Huh? So first visit, we get a value of 2, right?
yes,
Every visit,
we get the average of 2 and 1, so 1.5,
2 and 1 end.
and 0. Oh, wait.
So we have this state,
Yes.
and the state again, and the state a third time. So we have 3 values that we're averaging together. So we get basically 0, 1, and 2. And so our average is 1. Okay? Assuming these are all positive, clearly the every visit has to be less than the first visit. So it can't be that, it is biased in the sense that the expectation is not going to be equal to V of S for our single first episode.
why is the first visit 2?
The first visit, so here's the state we're in, and we've got a reward undiscounted of 2.
Okay, so it's first visit, like until you leave. the state.
First visit is first time you get to the state all the way till the termination. Right? So we always go from the state until the termination because that's the total discounted reward. Sometimes, like over here, if we look at S2, it's ignoring stuff that has happened prior to that. Right? We only count once we first get to S2. We don't count any previous rewards. Does that explain that? So this is biased, but as you start adding more of these episodes, it converges to the correct value. So after let's see how I want to write this. Let me say words first. So if we do n episodes, then our expectation, summing all those n episodes together, is that we're at n over n plus 1 of the true value. So in fact, after one episode, we're at half of the true value. After n episodes, we're at n over n plus 1. And as n goes to infinity, we're going towards the true value that we converge towards. Does that make sense? So let's say the expectation after of every visit from 1 to n equals and we'll throw in a pi here because we're evaluating a particular policy.
I don't understand what you're taking the expected value of.
So I'm taking the expected value of the average of all of our every visit estimates.
So just that over 2 basically. Oh, I guess in this case.
That total, that total averaged
Okay.
would, if we talk about one episode, be half of the true value in expectation, and over n episodes would be n over n plus 1 of the true value.
Can you explain the n plus 1 term again?
Like, why is it n plus 1, or?
When the approach is like large number, I feel like it's going to be
Right. The limit as n approaches infinity is going to equal v of s.
Yeah, that's right. But like, why is that specifically n plus 1? Because it could be n plus 2.
So I am stating this without proof that it's n over n plus 1.
Okay.
So we'd have to run through the math to do it, which I don't want to do. Okay, so I am stating it to give you an idea of why it is we end up converging.
Is this n over n plus 1 only for our given MVP? Or I'm thinking
Any NDP, this is the difference between the every visit and the first visit.
Okay.
Okay. What is our expectation of first from 1 to n? Josh.
1.5 or 1.
So in this case, it'll be 1. And in the general case, right, it's going to just be v of s. Right? In this particular example, it'd be 1. And in the general case, it's going to be whatever v of s is. Because every time we take an estimate, it's our true estimate of v of s, and we take any of those, and it's still expectation v of s. Okay. Our variance, which one's higher and lower? Right, the variance, you know, which one have more extreme values? Sina.
First.
Because?
Because you're not like taking the average of, like if you're basically doing it off of like 1.
Okay, so let's just prove by a single example. So our every visit value here is
2.
and our first visit.
First visit is 2, everyone is 1.
Yeah. Well, every visit 1 and the variance. If we have more of these are smaller numbers, right? We have smaller numbers thrown in there, so we're going to have this smaller variance. So less, more. So which do we want to use? Daniel.
Can't you do every and just like multiply by the right factor to make it
had never considered that.
If it, yeah, depending on else.
Depends on the probability.
That sounds plausible to me. Yeah.
What
Or-
are you using these for? What's your goal from this?
So our goal right now is just policy evaluation, but of course we don't normally just want to do a policy evaluation. We want to do policy improvement as well.
So you want to find the value function?
Yeah, we want to find the value function.
Okay. So then it shouldn't matter which one you do.
As long as we're willing to go to infinity, you're right.
No,
I mean,
but this
in it-
is the bias that you're talking about in the every visit.
Uh-huh.
That's the bias for the average of every visit reward, right? That's the bias of the average reward that you're getting, but that's not the same as if you're trying to calculate the total value.
Well, ignoring Daniel's suggestion for a moment, what we have as our estimate of the value is our average of all the rewards.
Why wouldn't you just keep track of all the rewards and then average over all the episodes? Well, I guess that is the same. Yeah, you're averaging over all the episodes.
Yep.
So then it should result in the same value, like it does here.
In the limit, it will, but let's look at an example. Let's see. In the limit, it will, but it won't in the small, right? Because, I mean, let's just look right here. Our first visit one's going to give us a 2, and our every visit's going to say a 1.
But we want the 1. Right?
Well, but this is what we happen to roll,
Yeah.
right? In the sense that we Monte Carlo'd, we Monte Carlo'd it out.
Yeah.
And so it's just happenstance that it turns out that V of S is 1, and this is actually more correct, right? If we looked at all possible rolls that we could have done, our average over those all, weighted correctly based on probabilities would have been 1. And the every visit one would have given us a 1/2. So over time, the every visit, as we continue over all of our episodes, would have increased to 1. So having a smaller variance can be useful. We'll see some examples later on today where you could have an infinite variance, which is not so great. In general, people use every visit. So the first visit has been more studied and is more theoretically sound. In practice, everyone does every visit. So, and part of the reason for that is you have to have, not a lot, but some special code in there to handle first visit. Every visit is really simple. Just keep processing from the end of your episode back, discount, back, discount, back, discount. Don't bother seeing to check, does it exist somewhere previous in there? And especially since you're going from the back towards the front, because you're going to do this incremental discounting, right? Take this reward, assign it for S1. Discount it, add R3, assign it to S2. Discount that. Does that make sense? Sean?
In the every visit 1 to n, what is n again?
N would be the n episodes.
And so
So what we've done is we've got multiple values for a state, and we are then averaging all of those across these episodes.
okay,
Right.
so in this example where you have 1 episode,
Uh-huh.
we're running through it, is S1, is n 1 or is n
This is n is 1,
Okay.
and we get 2 values for S1.
Okay.
And then the next time, when n is 2, we might get 30 values for S1, or you might get 0 values, or who knows, and we just average them up. And by the way, one slight mathematical trick that I really liked Vern showed me. So we talked about the fact that the percentage of zeros, I said the percentage of zeros is wrong, and I lied. So you asked, Dave, the numerator is getting bigger, right? But the denominator is getting bigger too. Doesn't that account for that? Right? We were basically looking at the fact that in this particular case, half of our episodes should give us a reward of 0. But in the every case, all of the episodes contribute a reward of 0, right? And so how did that work? And let's just look at that. Right, so this is the fraction of 0 rewards. In the first visit, let's say it's half is the chance for getting a 0, and out of all of them. So half or 0, and 1 in the sense of all the episodes. So the denominator was the number of episodes, the numerators are the number of episodes with a total reward of 1. 0. Total reward is 0. Right, does this make sense? This is the first visit. And in the every visit, let's see. Let me look at how I was looking at this. So I think I was describing on Wednesday was in terms of episodes. So all episodes have a 0. So basically we're increasing the numerator, but we are also increasing the denominator in terms of how many numbers do we actually have, right? We certainly have some number per episode, at least 1. And one way we can look at this is let's see how I want to look at this. So trying to think of how I described it on Wednesday and how I describe it now. So half of the episodes are of 0 length. And so we'll have half of them will, so this is the number of ones is kind of along here in this column. So half the time we have a 0 ones, a quarter of the time we have 1 ones, an eighth of the time we have 2 ones, and so on. Right? So if we look at the
Is it half about that? Because when we said that, when we have exactly 1, it's 1/4. Oh, I'm sorry, I see.
yeah, we do have a 1/4. We fixed that one. That one's correct here. Yeah.
Well, we could want to count the number of numbers and not just the number of ones. So it'd be half times 1 plus a quarter times 2.
Yeah, let's look at this. Let's call this, well, so this is the number of numbers. And this column is the number of ones. So we want to make sure we get every one of the ones. So 0 ones, 1 ones, 2 ones, 3 ones, and so on.
So then should it be half times 1 plus a quarter times 2 plus an eighth times 3? Because otherwise the math won't work.
I always do like the math to work. Let's think. So half the time, yes, so if we have an episode with 0 ones, that contributes 1 number to our set of averages. If we have 1, it gives us 2. If we have 2, it gives us 3. Like here, we have 2 of them, we have 3 entries. Okay. Thank you. And just looking at the sum, this was my problem on Wednesday, I consider, oh, that's not too much, but it turns out this works perfectly. And basically what we're doing is looking at this in the limit. Okay? So the question is, how do you evaluate this? And this was the part I really liked. So this is equal to 1/2 plus 1/4 plus 1/8 plus. So we took one of these 1/4s and we have 1/4 left back. So this is plus 1/4 plus 1/8 plus so on. And now we've used two of these 8ths and we have one left. And so we could do an 1/8 plus a 16th plus. Okay, you with me so far? So we've broken this basically single row up into multiple rows, each of an infinite sequence. And this then is equal to, oh, give me something, Justin, the first row. Half plus, sorry, not this row. This row, half plus 1/4 plus 1/8. Infinitely.
Would be, isn't it 2?
If there were a 1 there at the beginning, it'd be 2.
Oh, then 1.
Exactly. So this equals 1. And then plus 1/4 plus 1/8, so on, is basically this summation, but we lost a half. So it's 1 minus 1/2. And this one is going to be that entire summation minus 1/4 and a half. So this is going to equal 1 minus 3/4 equals 1/4. And we sum all this, and we get 2. And so basically, we're saying the number of episodes on the top, because all the episodes have a 0, divided by the total number of numbers. So this is going to be 1/2, or the fraction of all the numbers we have that are zeros, or that are zeros, is going to be half of them, which is what we originally wanted, right? So
it's basically the Poisson distribution.
it's
A Poisson distribution.
a what distribution?
Poisson?
Is this a Poisson distribution?
Yeah.
Could be, that's interesting. Does it, so with a Poisson distribution, don't we have a binomial factor in there somewhere?
Yeah, but like I simply can be converted into each other.
So, all right. Anyway, that was just addressing, Dave, your question when I said the number of zeros is going to be less, not equal to 1/2. Oh, really? Oh, wait, you are. Oh, yeah. Sorry, Dave. And you're the one, okay. All right, so, yeah, you are. And thanks, Vern, for the, and whoever else was helping you for coming up with this. The other Daniel, who's not here, he's sick. Okay. All right, so where are we now? We've talked about every visit. We've talked about first visit. We may switch back and forth between every and first as we've gone in the class. In practice, use every visit. And that identity that we had over here, we probably could generate from this little picture pretty nicely, getting rid of 1/2 and replacing it with x.
When you do every visit, you still do the discounting, right? It's just in this case, omega happened to be 1.
Gamma,
Sorry, gamma happened to be
yeah, gamma happened to be 1 in this
1. But you
case.
would still do that.
You'd still do the discounting. Yep. All right. We did see on Wednesday that just having the state value function is not very useful for coming up with a greedy algorithm, right? It's not going to help us improve our pi. In order to have a greedy algorithm, we need the Q function. Because without knowing the dynamics of the environment, we have no idea, knowing the value of this state and the values of the other states, because we don't know what we do is going to take us where and with what probabilities. So much better to just know, if I'm in this state and I take this action, here's what it's worth. And if I take this other action, it's worth something else, another action worth something else, and then I can take the maximum. So we like those Q functions. But in order to get valid Q functions, we need to have episodes that have every SA pair. Yes? Okay? Because if our And we need to figure out how to do that. And so the way we talked about on Wednesday was exploring starts, right? We basically say, start in a random state in action, and then follow your policy. And by starting in a random state in action, that means we're going to get episodes that give us values for every state in action pair. Is that clear? So the exploring starts. We basically start in a random state, take a random action, and then we get the rewards and we start following our policy. So okay. If you could do this, this is great. If you're in a real environment, as we talked about, you might not have your choice of what state you're going to start in, or your state and action combination. You know, if you're playing a video game, it's harder to start in a random state, for example. So we need some other option for how we can still make sure we get values for every state action pair. So we want estimates of Q of our policy with our state and action pair for all of our states and actions. Exploring starts was one possibility. One's not always going to work. So what else could we do? Kaki, thoughts?
Could we change our policy?
Okay, change our policy to
Visit a certain state.
well, we don't get to choose the states from our policy, right? We're given a state, and all we get to do is choose actions. But what we could do is have a policy that has a non-zero probability of taking any action. So, like an epsilon greedy is one of those, right? So a soft policy is defined as one where pi of s comma a is greater than 0. Okay, for all states and actions. And epsilon greedy, right, is a soft policy. So this is just like we did with, let's say, the bandit, right? Where we would have some non-zero chance of trying any particular action. And this way, Monte Carlo, we do it long enough, and we're going to get our Q's to converge for all states and all actions. And of course, the higher epsilon is, the faster that will happen, because the more you're going to visit some of these states that your policy otherwise wouldn't choose. But on the other hand, the lower your value is going to be because you're doing stupid random things. I suppose that's not necessarily the case. So can you come up with a setting epsilon to 1 gives you better values than epsilon of 0? Anyone? That is, really, the random policy is better than this policy? How about the policy where you jump off the edge, try and leave in grid world, right? The deterministically stupid policy, a random policy beats that. There you're only randomly stupid as opposed to inherently stupid. So it's not always the case that an epsilon greedy policy is worse with epsilon higher. But in general, as you're trying to progress towards better policies, a higher epsilon is going to be worse. So we are going to look right now this epsilon greedy, and this is what's called on-policy learning. Basically, we're following a policy to explore our environment, and that's the policy we're interested in evaluating and improving. So the policy that we use to interact with the environment is the same one we are evaluating / optimizing. And this is kind of weird because why are we making this distinction? I mean, why are we saying this? Because we're going to later move to off policy. So we will introduce this idea of having two policies, one of which we use to interact with the environment, and the other of which we're actually trying to improve. And they'll be different. So, but currently, we're on policy. So, I guess what we want to know is I don't know that it's worth showing this, but let's see. I guess what we might want to show is that epsilon greedy is among the soft policies, epsilon greedy will give you the best result. Let's think about that a second. So actually, first off, let's just define what's an epsilon greedy policy. So we want our policy to be random, most of the cases. And let's actually, so let's say this, given pi. Let's look at pi prime. So pi prime is epsilon greedy with respect to pi. Right? So Shannon, how do we want to define this?
Some fraction of the time you want to follow pi, and the rest of the time to act randomly. I don't know where you're going to generate that random number from.
All right, so let's do something like this. Let's say we got epsilon here, right? Epsilon is our value here. So let's make it something like so epsilon at a time we want to be random. So epsilon, a total of epsilon at a time we want to be random, right? So we want to divide that by the number of actions so we can spread it around all of the different possible actions. And I'm ignoring here the fact we might have some actions that are only defined for some states. I'm going to assume we just have a global pool of actions that are valid for all states. So define this if A well, let's look at it. What's the rest of it? 1 minus epsilon of the time we want to follow pi, right? So I'm going to say roughly 1 minus pi or 1 minus epsilon because we need to throw in a little fudge factor there. But we want to do this if A is what? If we've got pi, and let's say we know q sub pi, okay? So what would it mean for pi prime to be greedy with respect to pi?
How can you be greedy with respect to a policy? How can you be greedy with respect to the state values?
So we have a policy that is given our action values, right? So which is the best action to take from state S, according to pi? Sorry, given that we have pi and we know its values, what's the best thing to do from S? If I tell you that q pi, there are two actions. What's the best action to take?
First one.
Right, because our q value is highest, right? So if the action we're talking about is the largest, the A that gives us the largest q value, then that one we want to do most of the time. And we want to set a random, a small value, small probability otherwise. I know it's common to put the if above the otherwise, but I'd have to rewrite too much. Does it make sense or not make sense?
The sum of your probabilities is the one.
Okay, we'll fix that in a moment.
So is it basically like epsilon greedy, except it's smarter in the sense that if it knows already good actions, it's more likely to take those?
So it's epsilon greedy in that it is, the epsilon gives us the non-zero probability of taking any action, and the greedy is it takes the best value that it knows of in the original policy. So in the original policy, if we're in this particular state, what is the best action to take? As we know from the q pi, take it. Otherwise, we have this small probability of taking any other action. And yes, these don't match, and the reason is that with this same probability, we could choose this action either greedily or non-greedily, right? This is the greedy chance of taking the action, and then the non-greedy chance of taking the action is epsilon. So we've got the cardinality of A total actions. This then will give us size of A minus 1 times this. This will give us one more times this. And so it'll give us a total of epsilon added to the 1 minus epsilon. Does finally sum to 1. So, question?
I'm not sure how to articulate it. It's like the if condition after the,
Here?
yeah.
It's of course very confusing that I'm reusing A for two things. So let me fix that for a moment. We'll make that an A prime and that an A prime, right? So this is the best action to take from S, right? Given the values we know of pi. This isn't necessarily, so this is not equal to well, let's see. The max A what do I want to say here? It's not necessarily what the policy would have done, right? This is really what I'm trying to say here. So the policy might or might not have mostly chosen to take this action. But when we evaluate the values, it turns out that's the best one, which is why we're doing the greedy.
Just to be clear, the A of the pipeline is chosen randomly from all the possible.
Which A?
Like in the pipeline estimate A, like are you assuming like you're at
So we are defining for all SA pairs. So every single SA we need to come up. Now when you define a policy, right, there's two ways to do it. You can ahead of time enumerate what all of these probabilities are, or you might just on the fly evaluate it. It doesn't matter which one we do, but it's defined for every SA pair. And so for that given SA pair, we're going to look and say, what did we determine our Q pi's were for that S for every A? Find the best one, assign that here. With high probability, assign the other ones with non-zero probability.
Why does the probability assumption one again? Or how does
You mean why should they or how do they? The how do they is, because we agree they should, right? So we've got this many non-greedy actions, yes? And so we're going to multiply this by epsilon over the size of A, plus 1 minus epsilon plus epsilon over size of A. If I take these, I get epsilon. And then 1 minus epsilon plus epsilon. Gives me that. Okay.
So
Mazda.
could you review just soft policy just means something that doesn't rule out any action?
That is exactly what soft policy is. Soft policy, so a hard policy you can think of is sort of like for neural networks, if you did neural networks, a softmax, which is this soft maximum versus a hard. But it's hard in the sense of nothing is ruled out. We have non-zero chance of doing anything. So this just ensures we're going to visit everything. Right. There's a cost in that we're optimizing this policy, which will have the behavior that a small portion of the time will pick a random action. And so that probably will not be as good as a policy that chose the best action, right?
So the pi prime of epsilon greedy with respect to pi, is that the new pi that you then optimize on? Or like?
We're going to then do this iteration step.
Right, so
right?
in this case, each new policy is like the epsilon greedy version of the previous one?
Huh? Okay. So it is exactly as we did in the dynamic probing case, where we will go through this, right, evaluate step, which will give us, in this case, Q pi 0, and then we will go ahead and epsilon greedy, and this will give us a pi 1, and we keep going from there. So let's look at the code for this. Right? Let's just kind of work through how we actually do this with Monte Carlo. And I'm not going to assume any. I'm going to assume, let's see, which would be easier. We'll probably do every visit. And I'm going to do like we did originally with the dynamic programming and just have sort of an array of numbers. And we'll take the average and we'll ignore the fact. We won't show you this rounding average. Okay? So we want to have Q of SA equals some real, right? For all SA. So that's our estimates. What else do we have? Oh, yeah, so we'll have our let's say, returns. So it would just be an empty array. Okay, so we'll keep a list, basically, of all the returns for every SA pair. And the Q, we'll just calculate as the average of those. So what do we want to do? And I guess, what else do we need? We need a pi. So let's just get given, we'll get given some pi. Okay, and we'll, as we did before in the policy improvement, we get some starting pi, and then we'll just go from there. So what's the first thing we want to do, Matt? It's Monte Carlo. We're in the mine. We're at the beginning of the day. We're ready to roll. It's the first thing we do.
Evaluate a current policy.
Okay, evaluate our current policy. And how are we going to do that?
By evaluating the actions in different states. And
Okay.
recording their rules.
So we need to interact with the environment, right? So we need to generate an episode. According to what policy? Yeah, we're going to use the pi we have, right? Okay, so we generate an episode. So that gives us what? S0, A0, R1, S1, A1, all the way to, let's say, S, T minus 1, A, T minus 1, and our terminal RT. All right, we got our episode. Now, Dave, what do we want to do with our episode? Kind of high level, what do we want to do?
So we generated an episode according to environment. We just want to follow it. Like we want to follow according to our policy.
We followed according to policy. We did it. We interacted with the environment. Here's what we got. We got our list of states and actions and rewards. And now we're done.
So now you want to improve it.
We want to improve it. So what exactly are we trying to improve here?
The Q,
Okay, the Q. Sounds good. Okay, and Q is just going to be an average of the returns, right? So as a hint for what's coming up, right? Q of SA is going to be average of returns. Right? We need to do some discounting, and so it's going to be much easier if we walk from the back to the front, so that we can discount by a gamma each time, rather than have a discount like this one times this huge gamma. It would just be a lot more complicated, right? Because the S0A0 is going to include this RT, and the S1A1 is going to include this RT, and the S2A2 is going to include the RT. So let's just calculate the RT first and move it back. So let's do something like G equals 0. And now let's go through another loop for every state action pair, right? For what? T equals T minus 1 to 0. Let's try that. So now we can talk about S sub T, A sub T. In fact, let's talk about that. So results of S sub T, A sub T. In this case, the first time through, that'll be that one, right? Nick, what do those results equal for S sub T for the last one?
What do the rewards equal?
What's the reward?
0 for the terminal.
After we get this reward, we're in the terminal state. But this was our swan song return, right? Or there we go, our swan song reward, right? So getting into the terminal state, we're allowed to have whatever reward we want. Once we're there, nothing else. This was our last reward.
Right, so, RT.
Let's just sort of say append to that RT. So I agree with you, we want an RT in there. So actually RT plus 1, because right, we always have a state and an action at a time step when we get the reward on the next time step. And that fits with you, right? T minus 1, T minus 1, we get a T.
Is results supposed to be returns? Are those supposed to be the same?
You know, that'd be great. What should we call it? Returns or results? We'll call it returns, because it's the discounted return. Thank you. So that's great for this one. But if we go to the next one, S of t minus 2, a sub t minus 2, should we just get reward of t minus 1? No, we need to get our discounted rest of the reward. So we can do that with something like alpha g plus that. And then g equals alpha g plus RT. Ideally, we'd switch this order and not recalculate, but. Right, so basically, this will give us our discounted reward. This will always keep discounting alpha, 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 alpha. So by the time we get to here, we'll have applied alpha, capital T plus or minus 1 times correctly. Shannon.
So when you're resetting G, should that be RT plus 1?
It should be exactly matching this, yes. Thank you.
So like for the return, is that basically like a matrix of like a collection of like all the rewards for each corresponding state and action?
Yeah, it's going to be a list indexed by SA.
Yeah. So why would that be ST, AT in that case? Shouldn't that be like a separated? Because like let's say you can, for example, start from S1, then go back to S1 at some point, like during the time. So
This STAT is going to be first this pair, and then this pair, and then this pair, and then S1A1, and then finally S0A0. Yeah, it's a lowercase t, sorry about that, as opposed to uppercase t.
There's no guarantee that we'll have updates for every SA pair, though.
We for sure will not. We will have updates for every SA pair that exists in our episode.
So that's what the outer loop is.
The outer loop is we're going to keep observing the minor, keep doing episodes and seeing what happens. Okay, we're not quite done, right? We want to say something like Q of SA equals the average of returns of STAT.
And that's outside of the for loop, right?
No, that's in the for loop. Yeah, we might as well keep it in the for loop. That way we're only doing it for the STs and ATs that we've actually hit. Right? There's no reason to be updating Q for any other pairs than the ones we've gone over. It is true in the every visit, we'll have done the average more than once. I mean, theoretically, we only do it the last time. And then the last thing we need to do is update our policy. We can update our policy right now. Right? We have a new Q of SA, and we could just say, well, basically, is this QSA better? There's two ways for you. One way we could just say is, let's make it pi prime be greedy with respect to these Qs. Okay? So we're doing very slight modifications, a little bit of policy evaluation, like one actual entry in one episode, and then an update to the pi prime. Okay? But anyway, by the time we get back to this new loop, we will have updated pi. So basically, update pi. Okay? And we can do the updating smartly, because we can basically say, I don't have to update any other state action pairs, just the one that I touched. Need I look at? You had a question?
I think Manu asked me, is the Q outside of the for loop, like the inner loop?
Yeah, this is in the inner loop. And the reason it's in the inner loop is that way I know which SA pairs I have. So this is S sub t, A sub t, S sub t, A sub t. Because otherwise, if I'm outside the loop, like I got to try all STs, ATs, and there's no reason to do that because most of them didn't change. All right, so that's it for today. We will continue on with Monte Carlo, and we're going to hit a course off policy on Wednesday. See some of you in the cafe, see others in my office tomorrow afternoon.